Okay, so let me put this here. This tutorial will be about an introduction to probability, and it's basically a reminder for people that have not seen it so well, but it's just a brief reminder of each topic and in a very basic way. The first part is what's probability, and just to talk the same language, the probability can be thought as a function that takes an event from a sample space and it gives you a value from 0 to 1, and that value from 0 to 1 is what we call probability. And obviously the probability of the empty set, or the probability of nothing occurring, is 0. And an example of this is when you have dice, you have 6 possible states, and an event, for example, can be defined as when the dice is equal to 2. So when x is equal to 2, that's my event, and that event has a probability of occurring that, well, I'm sure you all know, but is 1 over the number of possible states, that in this case is 6. So it's 1 over 6.
Sorry, Carlos, are you sure it's screen?
No.
Oh. Okay.
No? Okay, but
Yes.
Nothing that I said now really needed the slides. But okay, so just to repeat myself, the probability is a function that maps an event in a sample space to a number between 0 and 1. And a very easy example is the dice, in which, for example, you can have the event of the dice throwing a 2, and that's 1 of the 6 possible states, and therefore the probability is 1/6. There's properties with this probability that we just defined. And for example, when you have the union of two events, that for example, A can be the dice throwing a 2, and B could be throwing a 3. And the probability of the union is the sum of the probabilities, but you need to subtract the part here where the probabilities the events overlap. In the case that I just said, this overlap is 0 because you cannot possibly throw one dice and obtain a 2 and a 3. But for example, if my event A is to obtain a 2 and my event B is to obtain an even number, then those two can be simultaneously correct, and therefore there's an intersection here of the events, and therefore you need to subtract the probability. And what happens when A and B are mutually exclusive is basically what I said in the beginning. When you have throwing a 2 and a 3, those events cannot happen at the same time, therefore they are mutually exclusive. And when that happens, the term here that is subtracting probability just goes to 0. Okay, this is a little bit more complicated. We will here I put it in reverse with respect with the picture. Sorry, this should be the probability of an event A given an event B. Okay, so what this means is which is the probability of the event A occurring given that I already know that B will occur, or that it has already occurred. For example, which is the probability of my number that I obtain when I throw the dice to be odd if I already know that it's a 2, or the opposite way, which is the probability of being a 2 given that I already know that it's even. That will change the probability calculation. And basically what we're doing by doing that is that given that the event B already happened, we can think of the sample space not to be the whole space, but just the part that has B. Okay, so this is the total of possible cases, given that B already happened. And which is the probability of A in that space is just this intersection. So the probability of A given B is equals to the probability of this intersection divided the sample space, that in this case is reduced because I already know that B happened, and that's why you are dividing by the probability of the event B. Did you understand that part? Everything clear with that? Christine, did you understand this part? Why the probability of A given B is equal to this? No? Daniel, did you understand why the probability of A given B is this expression here, or?
Yeah, because it's like you said at the beginning, it's like 1 over something. So like P, A, and B is like R1, and then B is the total.
Yeah, exactly. Yeah, that's a way to say that is easier to remember, because if you don't think it as that, you will forget this expression very quickly. That's how I remember the expression. And you can already saw here that if I, instead of putting P, the probability of A given B, I put the probability of B given A, the intersection will be the same, but the only thing that will happen is this part in the denominator that will be the probability of A instead. And therefore, we can conclude that the probability of A inter B is the probability of A given B times B, and then the probability of that is also equal to the probability of B given A times the probability of A. This is because we can do this previous expression, but with the A and B in reverse, and the probability of A inter B and the probability of B inter A will be the same, and we can obtain this expression. This is known also as the multiplication rule. And another thing that is very important here is that we can, given these probabilities and having already a probability distribution, I didn't talk here about the probability distributions, but I think you already know them. In one TA I talked about them. You can calculate this expected value. For example, if your probability is the probability of winning money by throwing dice, and the number that the dice ends up is X, you can calculate the expected value of your rewards. No, not rewards, but your price in the casino by doing this. And actually, if you calculate the expected values of winning something in every game at the casino, you will notice that you will always lose in all of the games. The casino is made like that. The only thing in a casino that has a good expected value, because it's a little bit more deterministic, is these coin machines, because by law they need to release some amount of money in a time period or something like that. So that's the only way to win money, because all of the other
Question. Sorry.
yeah.
It's kind of intuitive, but I guess that if so some people win a lot of money in the casinos, like sometimes. So and I think Carlos told us at the lecture that with these kind of things, as it goes towards infinity, you move to the average.
Yeah.
So if you won a big amount of money, the best thing for you to do is to run away, because then if you continue playing, it's going to go back down again.
Exactly.
Yeah.
The more you play, you will regress to the mean. So if you already won money, you basically need to go outside the casino and leave and never play again, because you already cheated the system. Yeah. And there's two types of expected value. The one with discrete variables, that makes more sense, for example, in the casino scenario, but you can also do it with continuous variables. That makes sense for many other situations. And the expected value is not only calculated in the variable x. Actually, this x could be a function, for example, g of x, and you're calculating the expected value of a function of a random variable, and what you only need to do is to replace this x with g of x in both places, here and here. And then you can calculate the mean of whatever function you want.
Can you repeat that again? I quite don't understand that part.
Yes, that here I'm calculating the expected value of the random variable, but you can also define another random variable, for example, y, that is equal to a function of the random variable x. And then calculate the expected value of y, that would be the same of the expected value of g of x. And by doing that, you replace this x with the y, but the y would be a function of x, and then you're calculating the mean of a function of x, for example, g of x, by just replacing this by g of x.
All right.
Think of it that as an input. This x could be whatever function you want, and it ends up here. That's it. And not also here, just here. Well, the same for the discrete random variables, of course. Okay, so now we'll do the activity. Let me think of it. Okay, so the first activity is something that you need to program by using random numbers. Here I put it between 0 and 1 because that's what I thought this graph could do. Because you can simulate this circle between -1 and 1 and have the full circle, or just have the quarter of the circle. And by calculating the amount of points that ends up inside the circle, you can calculate or approximate pi. This is actually a way to approximate that is called Monte Carlo methods. So the first activity is that should be very quick. And the second one is to prove that the variance is defined as the expected value, and here, as you can see, I didn't put x, I put a function of x, right? And the only thing that I changed here is that this is now the thing I want to calculate the expected value. And you need to prove that the variance, can be written as this thing here. Yeah, and basically that's the activities. I'm not sure if you want to do the activity all together or be separated in groups. What do you think is best? Maybe we can do it all together. What do you think?
Yes, I think it's very in group.
Better in group or better? Yes.
I think that we all together.
Yeah, same.
You don't care. Okay.
Yeah.
Some
I'm the
point in
same.
the semester, like all of our brains together is
All
probably the
together.
best option.
Yeah, we are all tired and don't want to think too much, but let's do it all together then. Well, at first, why this method is useful to calculate the probability of pi? Can you think why? Why, by counting the number of points inside a circle, you will approximate pi?
I guess you could get like an approximation or like a ratio of the areas of the square and the circle. And with that, you get, if you take that ratio, you're going to get pi at some point.
Yeah. So basically, if we have a, let's do it with a quarter circle. And this is 1, 1, and 0. And this circle has a radius of 1. And obviously, the probability of a droplet or point landing inside the circle is related to the areas. So to calculate the area of this quarter of a circle, you basically need to use pi r squared, but divided by 4. And the other area of the square is 1, right? Then the probability is equal to pi, as r is equal to 1, it will be just pi over 4 divided by the probability of the whole square, that is 1 times 1, and that's usually 1. And therefore the probability is pi over 4. And let's remember, this is the number of events divided the number of all possible events. So basically this can be approximated as the number of points inside the circle. And this can be approximated as all the number of points. Okay, so that's why pi appears here. Basically, you need to calculate the number of points that landed inside the circle, divide by all the number of points that you throw at this square, and that will give you pi over 4. And how can we program this? Do you remember which function we used to do a uniformly distributed number between 0 and 1?
With random point
Random.
no, doing import numpy as np and then putting np dot rand dot rand then
Okay. Okay, so from numpy import random. That works. Let's see. Yes. And then random
point rand, I think.
rand. And you can see here,
Number of random values.
this gives a random value, and it's a random value between 0 and 1, so uniformly distributed. Yep, perfect. And
In the shape that is the number that we want.
yeah, so let's say we want this amount of points. So these are the points. Let's put this as x and do it again and put it as y. And now, for example, Javier, do you know how to know if the points landed inside the circle?
No, I don't know. But I try to open my collab notebook, but it doesn't work. I'm sorry.
What doesn't work?
In my notebook, I don't have. I couldn't get the.
This?
Yeah, but doesn't work. My notebook. I'm sorry.
This? Well,
She can't open her collab.
Yeah. Yeah. But
okay, so someone else.
I
Mm,
The distance of the point to a zero is less than one, something like that.
yes. And the distance is basically x squared plus y squared. And that needs to be less than 1 because the radius is 1. And that will give me something that is true when the point is inside the circle. And to put it as a float, you can multiply by just 1.0, just 1 point. That will cast this Boolean number to a float. And then we'll need to do the... I'm not sure if I need to import it, but anyways.
You can use a sum. No, sum comes in Python.
Okay. So this divided by n give us this number. And that number, let's call it p. But this, as we already discussed, is pi over 4. So we need to plot 4 times p. And look at that. By the way, the number pi is 3.141592, etc. This that's with 10,000 points. Let's put more. You can see then when we put more points, you start getting well, better approximation. Let's plot the points from so I'm trying to do a circle here. I just write it. And I need to import pi. 0,2 times pi. And x circle equals to cosine sine. I'm not sure if I have showed this, but you can also define 2 variables in the same line by doing this.
No, this.
Did it work, Javier?
Yeah. Now I fix it.
Whoops. What was happening?
Is slow, my computer.
Mm.
Too much work for this semester, I think.
Clear. Here I'm not completely sure if or we can do it like this.
I think you can put like axis equal, something like that, and it gives you a.
Yes, but this is easier because I'm just plotting the quarter of the circle and it will do. Whoops.
Right.
Okay, so in this case I have so many points that all is blue. Puts less points there. So basically, we can also show the points that landed inside the circle by multiplying by this inside. There. So you have the points inside the circle, the outside of the circle. When you do the ratio of the points inside the circle with all the points, you get an approximation of pi. And obviously if we put more points, you start getting better and better approximations. And when you put so many points that the marker size is too big, you basically see like a disk with a blue background. It seems that the first time I ran this with a lot of points, it gave almost exactly pi, but now it's not giving the good approximation. This is obviously random, so every time I run it, it will give a different number. But yeah, that's a way to approximate pi, and this also works to approximate integrals. Because basically what we are doing here is trying to approximate the integral of the area under this curve. So by throwing points randomly, you can also approximate integrals, more complicated integrals. And that's something that is very useful when you have more dimensions. Here it's not that useful, but when you have like 100 dimensions and you can't integrate, and then just throwing points, it's a good way to approximate. And well, the last thing is to prove this. Let me another slide, sorry. Okay. So first, I just want to be sure that you understand what the expected value is. So if you have your random variable x, this can have a probability density distribution. This one is called f of x in caps, and here you are evaluating without caps. When you have x in caps, just to make sure that you understand the notation, but this means the random variable. And when you have it without caps, that means an instance of the random variable. Basically, here you are evaluating in points. For example, here you have x equals to 1. Here x equals to 0. X equals to -1, for example. And when you calculate the expected value, that is the integral of f of x dx, and you multiply here by the thing that is inside the expected value, And this integral is in the space of the probability. This is the sample space. And it depends on the probability density distribution. And what it gives you in this example is, for example, this value here. The most likely value of x is this that is at the center. So this will give you the expected value of x. But for example, when you do the square of this, okay, so the expected value of, now instead of just x, you put x squared. You're calculating this integral, but with x squared here. Okay. And this is known also as the first moment, because this is x to the first power, first moment. And this is the second moment. Well, this is not exactly the second moment, but this is the second moment. And I'm not sure if you remember, but there's a function. Well, if you saw probability, you saw a function that is called the moment generator function. Do you remember about that, Esteban?
Yes.
And do you remember what the moment generator function has that is very special? What can you do with the moment generator function?
I don't remember very well.
No?
But it's like a...
Do you remember how to obtain the moment generator function? It was an expected value, right?
Yes, it's an expected value
Of
multiplied by the variable.
So, well, the moment generator function is this. The expected value of e to the x t, and this is an additional parameter. And here is something that I was talking earlier, that this could be interpreted as a random variable, and it is just a function with respect to x. And then that means that you obtain, I'll put it like this so you can see it quicker. Okay, so let's say that the sample space is from -infinity to infinity. And do you notice which expression is this? Or is related with something?
Yes, it's like a Fourier transform.
Yeah, something like a Fourier transform, right?
Yes.
It's more similar to a Laplace transform.
Yes.
Right? So it's something like a Laplace transform. But the cool thing is that this exponential can be written in the Taylor series, right? And if you write that as a Taylor series, you'll obtain 1 plus x plus that 1 plus x divided 1 factorial plus x squared divided by 2 factorial, and so on. And you can separate this as the moment 0 plus 1 divided by 1 factorial, the moment of the first moment, the 1 divided by I forgot to put a t here. T. So you obtain t times t squared 2 factorial e to the x squared, and so on. And that's why it's called the moment generator function, because here you have the 0 order moment, here you have the first moment, here you have the second moment, and basically this is a function with respect to t. What happens if you evaluate this function in t? You delete everything and you obtain the first one. Then if you do the derivative with respect to t and evaluate with t equals to 0, you will remove this one. Let me rewrite that. I'll copy paste the thing from above. Are you understanding what I'm saying, or is this too weird?
I got lost.
Yes.
Christine, what did you say?
I got lost.
Do you know what a Taylor series is?
No.
No? Okay, so probably that's why, but a Taylor series, for example, if you have the function sine of x that is like this, it's basically trying to approximate the function by polynomials. So the 0th order polynomial is this one. You can think of it as just a line. Then the first order polynomial that can approximate the function is this one, that has the same slope as sine in this point. Then the second order polynomial will be the same as this one. And the third order polynomial will be something like this. Whoops. But the thing is that if you start adding more and more terms to this polynomial, you'll start obtaining more and more accurate representations of a function. And actually, you can, not with every function, but with a lot of functions, you can write the function exactly as the derivatives of the function and divided n factorial, that will be the polynomial that you want. So this in particular is called Maclaurin series, because it's with respect to a equals to 0. But in general, this is called the Taylor series. You have the same here, here. And basically you are subtracting A because you're centering your approximation in A. And the only thing that changes is this, and this is called the Taylor series. And for the particular example of e to the x, the derivatives of e to the x is always e to the x, right? And when you evaluate e to the x in 0, that gives you 1. And therefore the summation that is equal to e to the x is just x to the n divided by n factorial. So this is the Taylor expansion of e to the x. And as you can see here, we did the Taylor expansion of this e to the x and rewrote it as this. And now we just multiply this f for each term and distribute the integral, and we'll obtain that each integral that I have here is equal to the first, the 0th moment, the first moment, and so on, multiplied in the outside by t divided by 1 over 1 factorial plus t squared divided by 2 factorial, and so on. And that's how we arrived to this point. I'm not sure if it's more clear now.
Yes, thanks.
This, by the way, does not have anything to do with the activity. It's just something that I think is good for you to know. So, because this function is very useful. So now if you do the derivatives and so on, you can see that when you take the kth derivative of this function, and then evaluate in 0, basically what you're getting is the kth moment. So this is why this is called the moment generator function, because you can generate all the moments by evaluating this function. Okay, so that's one thing. And for example, if we look at the moment generator function for the normal distribution, because we'll not do the integral here, is this. So the moment generator function, or this, we'll call it m of x of t, is equal to, example, I know that this could be a little bit boring for the engineers. Bear with me a little bit. Okay, so for the normal distribution, we have the following. For the normal distribution. And we already talked that this moment generator function is similar to a Fourier transform, right? and is also similar to a Laplace transform. And that's why the moment generator function of the normal distribution is also something like a normal distribution, because the Fourier transform of a Gaussian is also a Gaussian. So to obtain the first moment, or the expected value of x to the 1, we already talked that we need to do the first derivative of this moment generator function and then evaluate in 0. Let's do that. So e to the x, when we do the derivative, is the same. But by the chain rule, we'll multiply by the derivative of this exponent. So we obtain mu plus sigma squared t squared divided by 2. And this expression needs to be evaluated in t equals to 0. And when we do that, you can see that this term disappears, and this one also goes to 0, and we just get mu. Now, if we do the same, but with x squared, we need to do the same, but with the second derivative of m of x, and then evaluate in 0. And that should be, well, the derivative of this times that plus blah blah blah, and that will give us something. And now we start the exercise. So let's remember the exercise is to prove that the variance, that by the way, by definition is this. The variance is because it is the standard deviation squared. X minus mu. Mu is the first moment. Is equal to the expected value of x squared minus this. So, how do you think we should start to verify this?
You could expand the expected value by the function.
Oh, I forgot to put a square. So basically what you're telling me is that I should do the square inside?
No. Even before that, you could do. We already know what the like that expected value is. We know it's the integral of what is inside times our probability distribution. So you could just expand that immediately.
Okay, so this is the integral of x minus mu squared and the probability of x that I will not put here. So to expand it, we need to solve this anyway. So let's not write it as an integral because it will be more text. But the intuition was correct. We need to do the multiplication here of the squared binomial. Okay, I hope everyone agrees with this. When you have x minus mu squared, that's x squared minus 2 times x mu plus mu squared. And I'm not sure if you have noticed, but the expected value is a linear operator. That means that the expected value of lambda times x plus beta times y is equal to the alpha times the expected value of x plus beta times the expected value of y. And why is that? Because basically we're doing an integral, so all the factors go outside the integral and the summations can be distributed. And that's why it's important that this factor here goes only to one part of the integral. So this only goes here. Because if we try to evaluate this in here, it will not work. Because then we are not calculating the expected value. The expected value is to replace this in this part. And then you can verify very easily that it satisfies this property. And now you obtain the expected value of x squared minus 2 times, because it's a linear operator, and mu is constant, a constant value, mu, expected value of x plus the expected value of mu squared. But mu is constant, as I already said, so it goes outside. So this is mu squared, the expected value of 1, and obviously the expected value of 1 is 1. And another thing is that the expected value of x is the definition of mu. And minus 2 mu squared plus mu squared is equal to minus 1 times mu squared. And therefore, and we arrive to our conclusion. Everything clear with this? Christine, did you understand the procedure?
Yes.
Yes?
Yes.
Okay, so the next tutorial, we'll start seeing the topics related with Markov chains. And they use these basic concepts of probability to well, you'll see when you see the classes, because I think they start next week. I will not be doing the summary of that yet. But basically what I want you to understand of this are the basic concepts, so you can go to the class and remember the basic concepts of probability. I'm sure there's a lot of tiny things that is good to see again. And I'm not sure, for example, if Javiera or Christine have seen these kind of properties or way to show the probability and expected values and the moment generator function, etc. Do you have a course in probability, Christine or Javiera?
No, in this way, but I understand the tutorial, so thanks.
Yes.
Also, the class with Carlos, we have a very useful information to understand that.
We probably talked some topics. I probably talked the same as Carlos in at some points. I didn't see the class, but probably he saw something similar. I'm not sure. Can you confirm, Javiera?
Not about Taylor. The this last process, but with the first, yes. And also, I don't know if finish the Markov. I don't know.
No.
But
The next tutorial will be about Markov chains, and probably
yeah,
the previous classes will be about that.
Yeah.
And that will be the topic of the last homework that is optional.
Yeah, there's homework 6, I think.
Yes, and it's optional, and if you have a bad grade, it will greatly improve your grades because it's only one exercise, and
Oh,
probably it will be about the same thing of this homework. What I mean with that is the Lotka-Volterra equations, but
yeah, okay.
seeing it as a Markov chain instead of a differential equation.
Yeah.
So if you understand the Lotka-Volterra equations in this homework, you'll understand what this other homework will ask, but with another point of view.
Yeah, okay. And Carlos, I have a question about the next tutorial with you. Is the next week?
It's
The
should be the next week.
Tuesday?
Let me verify right now. I think it's in Friday, but I'm not sure.
Okay.
Oh no. I remember now. Let me because the professor has planned that the next tutorial is about the project. I think.
Yeah.
Let me check right now to be sure.
Maybe it's the next Thursday
Mm-hmm.
because the next class is the Tuesday 30.
No, in an email, the Professor Carlos say that next Friday will be the something that he called office hours, and it's while we about the projects.
Okay, so
Yeah.
now I just checked, and the Thursday I'll have examples of Markov chains, and previously on Monday, you'll see a brief introduction on Markov chains, and on Friday we'll have an office hour or discussion about the project. So I think the professor asked you to send doubts and stuff like that about the project, so you can take advantage of these office hours, because I will already know what you have doubts and I can explain it better. So I'm not sure how are you with the time, but try to send the doubts before Friday so we can prepare and start answering questions about the project. Did the professors say something like that, right? Or did it just to me? Did he tell you to prepare for
In
the...
the announcement?
No, in class.
I think yesterday in the first when start the class, tell about
The office hours?
the last yeah, and the last class with he and the tutorial,
Hmm.
and also talk about the homework 6 that is the optional.
Homework, yes. So okay, that's all for today then. We'll see each other or hear each other uh, next week on Thursday and Friday.
Okay.
I'll end the stream